Yeah, my name is Chris Fuson. I work with Tom and Matt, George, and Bill. Um, and for the next hour, I want to go over how you will access and use, launch jobs on the compute resources of Summit. So first off, I want to give a kind of a high-level overview of what the Summit looks like, for this talk and the key pieces that we're going to talk about. So this is, if you imagine in the green dotted lines is kind of Summit and the big components that we're going to reference here. To the left is where we start. So this is our laptop or our computer, and we SSH into uh, Summit, and it places us on one of the shared login nodes. Those login nodes are, as we discussed, where you will compile, create directory trees, and submit your batch jobs. From those login nodes, you will use the batch scheduler, which we use LSF, and the command that LSF uses to submit batch jobs is bsub. Bsub will allocate your resources, the compute resources, and once allocated and you make it through the queue system, it will place you on a batch node. From the batch node, you can use the job launcher. Summit, we use JS_run, and that is how you will get from the batch node to your allocated compute resources. So a couple of things to note here. When you log in, you'll land on login nodes. I think there's 8, so you'll SSH to Summit, and it'll round robin you and do some load balancing behind the scenes and place you on one of these login nodes. But these are shared resources, so you're on a node with other users. When you submit a job, it will place you on a batch node, which is very similar to a login node, and it's also a shared resource. And all of your serial commands within that batch job will be executed on the batch node that you've been placed on. To get to the compute resources, you need to go through a job launcher. So you'll need to use JS_run. All right, so in this talk, I want to focus on the 2 main pieces of this that you'll need to understand to run on the compute resources. So the first is the batch system. So we use LSF on Summit. LSF is a batch scheduler. If you've used other HPC machines, this should look pretty familiar. It's very similar functionality and a lot of times syntax to PBS, Moab, and Slurm, and some others. But it'll allocate you. You'll basically tell LSF what you want, and it will allocate those resources for you. And another thing to note is that we allocate entire nodes. So while the login nodes and the batch nodes are shared, the compute nodes are all yours. So we only allocate a node to an individual job. The next piece that I want to focus on in this talk is the job launcher. So the job launcher is how you get from the batch node to your compute resources. On Summit, we use JS_run. JS_run is similar in functionality to app_run that we used on the Cray machines, to Slurm's srun, and to OpenMPI's MPI_run. It's similar in functionality in that it will take a binary and launch it on the compute nodes and let you control the layout, the task, what it sees and where it goes. But JS_run is a little different than some of those tools. So while LSF is pretty close to other batch schedulers, JS_run has some notable differences that I want to spend a little time on. So let's start with LSF. So this slide shows the batch script, just an example batch script, pretty simple. Hopefully it kind of looks familiar if you've used other HPC systems. The first line is the interpreter, so pound bang then bash. That will tell the system to use bash to interpret the script that you're sending it. The next lines that begin with pound bsub, all caps, those will be interpreted by LSF as flags and that for LSF. So the first line in this bsub, just to walk through these real quick, asks for a wall time of 2 hours. So that means that from the time that your job is allocated to the time it ends, you expect it to be under 2 hours. And you want, when you request time, for that time to be a reasonable time. You definitely don't want to go short, because the system, once it hits that wall time, will terminate the job. So you don't want to be in the middle of work while this terminates necessarily, but you don't want to request it way too long, because then you could impact how long you wait in the queue. The next line, the dash n nodes, request the number of full nodes that you need for the job. Again, we allocate full nodes, and we don't share nodes between jobs. You can get multiple nodes, but those nodes will be entirely yours. The end node syntax is a little, that's new for us from LSF. So for the Coral machine, so both us and Livermore, this LSF gave us this as an easy way to request nodes and not have to go through other syntax methods. The dash P, the capital P, allows you to specify a project. So this is a project that this job's time will be charged against. So basically, when we run jobs, we charge time based on the amount of time that the job ran and the resources that it used. So basically, nodes times the time that the job was in the queue from start to finish. The little o specifies the output file name, and the big J lets you name the job. So following the bsub, LSF will run through this script. It will, all of your #bsub LSF directives need to be at the top of the script. It will run through until it reaches the first non-comment line. So all the #bsubs, of course, will be seen by script as a comment, and LSF as a directive. Once it reaches one that's not a comment, it will stop reading for its directives. So the first thing I have here, this script is very simple. It just runs hostname. For the first line is a basic hostname, and the next line we run hostname through JSRun. So just to show the difference, what you would expect to see from that first hostname is a return of the batch, of the shared batch node. So you may see something like batch 2 or 3, because those are the names of the batch system, or those series of batch nodes. The next line you would see the name of a compute node, so something similar to H23N1, and in this case you would see two nodes. I only gave an example of one here, but those are kind of the differences. The first one would be executed serially on the batch node, and the next one we run through JSRun, so it would actually go out and be executed on the compute resource. When you submit this script, if you named this example.lsf, you would simply say bsub example.lsf. The system would give you a job ID that you see kind of similar below, and then it would return your prompt. So we went over some of these options, so I won't spend a lot of time here, but a couple of things to note. These are just options that we thought are common use options. I went over most of these in the previous example. Something to note, the first three, so the wall time, the nodes, and the project are required. So each job must submit, including one of these flags. The --J, I think you should also use for every job. If you don't specify the --J, the system will default to naming your job, not _specified. So that's not super useful when you look in the queue and try to figure out what your job is doing. It will by default name your output the name of the job as well. So all of your output would be named not _specified.o or something. So neither of those are real helpful. So I recommend naming the job with -J. So I think the first 4 flags are, you can add more, but I think those should be in all of your batch submissions. Going down, again, these and more are in the bsub man page. The last line here is the alloc flags we'll touch on a little bit later. These allow us to pass flags into the so the setup of the node. And so we can do things like set the GPU multiprocessing service, and we can change the SMT levels, the multi-threading levels with these flags. So another thing to note is the ability to run interactive jobs. So an interactive job, what we went over before was a batch job. So basically, you would create a script and you would submit it to the batch system, and you could go away and then come back later and check that, and it would run it as it makes its way through the queue, as the priority is raised, and as it gets to it, right? So an interactive job, though, allows you to allocate compute resources and use those interactively. So what you could do is say, I need 2 nodes. You would submit that as an interactive job. The system would return a prompt on one of the batch nodes. And from there, you can run any number of JS runs that you want to. It's very useful for debugging. It's very useful for, as we go, as you look after this talk and want to investigate layouts, it's useful for that. What it does is allow you to run multiple JS runs, or maybe even build, if your build is quick, make changes to your code in between each JS run without having to wait in the queue, because that adds some overhead and time. So basically what an interactive job looks like is in this black box at the bottom. You'll still need to, you'll use bsub, and you'll still specify the project, the nodes, and the wall time. Those are required. But you'll simply, instead of giving a file, a script, you'll use the key -I s, and then give it, the last line is the last option here is shell. So often you'll probably just want to use your $shell, which will load whatever you're running currently, which is probably your default shell. But you could also pass in bin bash, Bourne, or tshell, or whatever you may want. Once you submit this, the job will then have to go through the queue, so it'll immediately give you the job ID, and then it will wait. So you will not get a return until that job makes its way through the queue and is allocated those resources. Once it's allocated the resources, it'll tell you it's starting, and then shortly after, it will give you a prompt on the batch node. And you can see, running the same hostname example here, I run hostname, and it gives me batch1 because that's where I'm at. I run JS run, and you can see launches hostname out on the compute resources. So this is handy for investigating and debugging and looking at layout. So this table, I'm not going to spend a lot of time. It gives some common LSF commands. I think we went over bsub, which is how you submit. If you want to monitor jobs, we'll go over that in a second. That's bjobs, and bstat lets you look at those. bhist will let you investigate a little more detail of a job. Removing a job from the queue is bkill. Putting a job on hold is bstop, and bresume allows you to remove the hold from a job. So once you submit your job, I think the next big thing that you're going to want to do is monitor that job's progress through the queue, see where it is, why it's running, why it's not running, when it finished. So you can use bjobs to do that. So bjobs is similar to show qstat if you're familiar with PBS. It will, by default, just return your jobs in the queue, but you can say -u all and see the queue in its entirety. A thing to note about the queues, that we kind of think of the queues here in 3 pieces. We separate them kind of in mind with a section of running. So running jobs are allocated jobs. Those are jobs that have resources and should be being executed and active. The next section of the queue are the pending jobs. So these are jobs that have been submitted to the queue, through bsub, and they're sitting waiting on resources. Once those resources become available, LSF will consider those jobs for execution as resources become available. So they sit in pending. As they wait, they gain time, and they move up in the queue and increase their priority, right? The third section is the pending ineligible. So these are jobs that are not eligible for execution. These are jobs that are in the queue, but LSF is not going to consider these jobs when executing and looking to fill empty slots. A job could be in this section for any number of reasons. You could place the job on hold. You could have a dependency on the job to complete before, after another job. And so while the job's on hold, while it's waiting for the other job to finish, it's not eligible to run, so the system places it in this state. There's also policies that we set at the center to also that would also place jobs in this state, because we place limits on the number of jobs that you can have in the pending eligible state. And once you go over your allocation, we also note and change the priority, or limit the number of jobs that can get into a one. So you can use bjobs, with the command that I showed there to see the differences. But what I like the best is a command that we wrote here in the lab called jobstat. So jobstat will give you the separation of the queues. We'll show you the queues entirely in its entirety and separate it into running, eligible, and blocked, as you can see here. So if you run this on on Summit, you will see a much larger queue, but this is a small example of what you might see. You can see the running jobs shows when the job started, how much time remains, what the nodes look like that are allocated, how many are remaining. You can see an example here of the where a user did not specify a job name, so those jobs are named not specified. The next section is eligible jobs. So these jobs are eligible to run in the queue once resources become available. A thing to note in this section is that you can see the priority for eligible jobs. We boost jobs that are larger on the machine. That's one of our goals and requirements here at the center, is to run jobs that are bigger, that utilize more of the system. So jobs that are bigger get a bit of a boost. And so you also gain priority by waiting in the queue. So you can see a priority increase as it waits in the queue. And the jobs in this eligible section are listed in priority. Highest priority at the top and the lowest priority to the bottom. The block jobs, or as I was saying earlier, are jobs that are not available for execution. Those are jobs that that either you've placed a hold on, you've got a dependency, or in these examples, they've hit limits on the systems that we've placed to throttle jobs throughput for one reason or another. So the first example there where jobs is highlighted, this is what you would see if you're, say, over allocation, where we limit the number of running jobs that you can have. So in this case, this user has run into this limit, and so the jobs are going to be placed in the block state until that running jobs count is below whatever limit we've set. Once they're below that, this job would then be allowed to run into eligible, and then it makes its way through the queue and eventually run. The jobs per sched cycle, we set that for everybody. That's a limit for the number of jobs that you can have in the eligible section. So by default, that's 4 for everyone. If you submit 6 jobs, for example, 4 of those will be eligible, and the last 2 that you submit will sit in the block state until there's, until one of those jobs in the eligible moves into running, then one of the block jobs can move up. And we don't generally put a limit on the number of running jobs that you can have unless you're over allocation. So this is a quick view of the queue policy for Summit. You can see here where I listed the docs page, where you can see the policy for this default batch queue, as well as some of the other queues that are available. And it shows here you can see how we bin jobs based on job size. The larger jobs you see get a boost, so you see jobs that are from 2,700 up to the max of the machine get a boost of 15 days. And they can submit a job for a maximum of 24 hours. As you go down, the next group down, you can see from 900 to 2,700 gets a boost of 10 days and a wall time of 24 hours. And then the wall time is reduced after that. And those top 2 bins are the only bins that get a boost. Everything else doesn't get a priority boost. In fact, they get a smaller wall time by default. So by the time you get down to jobs that are in the from one node to 45 nodes, you have a max of 2 hours for those jobs. All right, so that's LSF and a little bit about how you request allocation on the machine, how you tell the system, I want this many nodes for this many hours, And so now the next step is to how do you run on those nodes that you are allocated. So before we go into JS Run, I want to go over an image that we use. It's a very high level image of a Summit node, not as detailed as the image that Tom gave earlier, but we use this just to kind of show where layout occurs on the job, where you will place tasks, and threads, and what is available, and where JS Run places those things. So to go over this image, because I'm going to use this as we move through the rest of this talk. So this is a single Summit node. You can see it has two sockets. You can see left and right are the sockets, and then at the top you can see the GPUs. So there's 3 GPUs per socket, and then going down, you can see the memory banks there on each summit. On each socket. You can see the XBus that connects those 2 sockets. And then within each socket in the blue squares are cores. So the dark blue square, and I have one highlighted and brought out just to help explain here. Those are physical cores. So each physical core is a dark blue, and then within each there are 4 hardware threads. And so we'll use this mapping as we go forward, this image, this diagram. A couple of things to note on the core and hyperthread or hardware thread numbering. So because the system will always return under normal, when you query it, it will normally return the hardware thread number. So regardless of the SMT level that we give in examples, we always use the same numbering, in that it's 0 for the first, the first physical core has hardware threads 0 through 3. So even if you're not using those hardware threads in the examples that you run on the machine, it may say, all right, you're on 001 and your next task is on 006, and that means that you're on core 0 and core 1. Another thing to note about the numbering is, if you notice at the bottom of each socket, we jump in from the first socket from 83 to 88 on the next socket. There is a core on each of these sockets that we set aside that is not accessible to JS Run. It's only available to system for overhead, basically overhead task. So we isolate that core out for system task. It's not accessible to you through JS Run, but it does impact the numbering. So if you're wondering, you run an example and you wonder why it skips from numbers there and why it doesn't go as high as you think it should on the last core, that's the reason. Is because we've taken a core, that last core, off of each socket and removed it from the pool. So I mentioned that we have hardware threads each core. So this is just a note on those hardware threads. So the Power9 supports 3 levels, so 1, 2, and 4, and basically that means you can activate 1, 2, or all 4 cores on that, or activate the virtual cores on the core. Sorry. So you can control this at the LSF level using the -alloc flags that I mentioned before. So if you use the alloc flags and say SMT1, it will activate only 1 of those hardware threads on the core. 2 will activate 2, and SMT4 will activate all 4. So by default, we activate all of we run in SMT4 mode and allow use of all 4 threads. It's my understanding that it's not going to slow you down. There's no overhead there that's necessarily going to impact your performance. In fact, having those threads available just allows the system, or if there's other tasks behind the scenes, to kind of spread out on those threads, and so it may help you a little bit. So I think it doesn't hurt, but it may help. But if you want to test, you have that ability. You can you can set those at the batch job level. And then after you set them at the batch job level, you can use JS_run to control the layout. But I think our default mode and maybe suggestion is just to use the SMT4 mode and then use JS_run to control the layout of those tasks across the resources. All right, so that is a little bit about LSF and how you allocate, and a little bit about what the node looks like, as far as our examples and what we're going to use to note layout with the various JS_run flags. So now I want to move into the job launcher, and so again, job launcher on Summit is JS_run. JS_run is the tool that you will need to use to get from the batch nodes to the compute nodes. So LSF will allocate the compute nodes. It will place you on a batch node. Anything in your batch script or your interactive batch job that you run serially, not through JS_run, will land on the batch nodes. Anything that you want to go to the compute nodes, you'll need to use JS_run. So JS_run, as I mentioned earlier, is similar to srun and MPI run and app run, but it is more different of those than say LSF is of the other schedulers. And one of the big reasons that it's different is this idea of resource sets. So a resource set is really the building block of a JS_run command and layout. It lets you organize a node and subgroup a node in a way that may make more sense to your job, to your code that you're running on the node. It's a little different than other launchers, but the idea is not too complicated. But it is a little different. So I want to spend a little time and go over the resource sets, what they look like and why you care about them. Under the covers, if you're familiar with C groups, basically a resource set is just a C group. It's just a kind of a small grouping of nodes and cores within a node. And the goal of resource sets is to kind of let you organize the node how it makes sense to your code. So you can subgroup a node into individual cores. You can group it into cores and GPUs so that those cores only see the GPU that you've placed in that group. Or you can say, I don't need this, and you can place a resource set across the full node and let your code worry about the mapping of tasks to GPUs. Let the code worry about if you care about the XBus connection between the two sockets and the memory, I guess, between them. So it kind of gives you a little bit of a power to do that. So a couple of notes and some limitations on resource sets. A resource set must be within a node. So it can't span multiple nodes. So at its largest, it can only be a single node. On the other end, it cannot break up a physical core. So on the small end, a resource set can only be a core. On the large end, it can be a node. And by default, the resource sets are all the same. So you will start 12 resource sets, and they will all contain the same number of cores and GPUs and look the same across the board. There is a way to change that, but we won't go into it in this talk. So a little bit about, as we go through this, these are kind of the key pieces that I think about when thinking about resource sets and how they interact with the code in a job. So I think when you're thinking about how you need to create a resource set, it's probably good to start with what does your code want the node to look like? Is your code able to able to say, all right, I have this many tasks, this many threads, and then I have this many GPUs. Let me figure out the workload among those and who talks to who. Or is it easier for your code just to say, all right, these two tasks, these two cores can talk to one GPU, and they will send work to that GPU. It all depends on what's easier for your code, what makes the most sense. So, but once you know what that looks like, if you want that breakdown to be 2 tasks to a single GPU, or if you want that to be 40 tasks to talk to 6 GPUs, whatever that looks like, you know what that will be your resource set, and that will be the step 1. From there, you can then decide how many resource sets can I place on a node using, keeping in mind what a node looks like. And once then you know how many per node, then you can take a step back and say, okay, now I need my LSF request to allocate this many nodes. So you kind of start with the code and then you back out into the number of resources that you need. All right, so now stepping into JS Run, this is a kind of a high level format of JS Run. The first line there kind of shows how all of the JS Run requests will look. Basically, you say JS Run, then you pass it the number of resource sets that you want. You use the -n number of resource sets. For the most part, everything after that is going to simply say, this is what a resource set looks like. So, so after you specify how many resource sets you want, then you say, each of my resource sets will have 2 tasks, 2 physical cores, and 1 GPU, for example. And then the system will go out and allocate and create resource sets that look like that for as many times as you want and start up task. You start up the process that you've passed it on to those resources. So for flags for JS Run, similar to other Unix commands, there are long and short flags. There's the long flags start with 2 dashes and are maybe a little more descriptive. And then the short flags are just a single character. So we went over -n a second ago. It specifies the number of resource sets. The -a will specify the number of tasks and ranks that you want to start per resource set. -c is the number of cores that you want to start per resource set. -g are the number of GPUs that you want within that resource set. And then binding the -b says to bind task to some number of physical cores. And then the last option there, the -d, is the launch distribution. So this is basically how you lay out, or how the system will lay out task, MPI task, or ranks between each resource set. So I've highlighted the flags, the number of resource sets, the tasks, the cores, the GPUs, binding, and distribution, because I think what we found is that it's good. It's a little verbose, but it's good for every JS run to include these flags. The system has defaults, but most of the time you're going to run into cases where those defaults are not what you want. So better to just specify what you want instead of taking defaults, and then and then you don't sit in the queue for a day and only to find out that the system did something that you weren't really wanting it to do. So now I want to go through some JS Run examples. And using the map that or the image that we went through earlier, I want to run through a number of JS Run cases and show how the system will lay those out. So this example, JS Run -n1 a.out. So this will start one resource set, and in that resource set, the system will run a.out. You can see in the mapping in the red box that that the system will create this resource set on the first core. Um, it will then launch your rank 0 on a thread within that core. Now this is probably the simplest, the shortest JS run that you can run, but we strongly recommend that you don't stop here. I think one key is what this gives you by default, and you can kind of see that it's really not much. You get a single core, and that's it. You don't really have a control over how many tasks are started here, how many GPUs you can see. So in order to do that, you can do what we suggest and expand your JS run command. So what you can do is instead of just in1, you can then describe what that resource set looks like. So we specify -a, which is the number of tasks. So we say in this resource set, we want it to contain, we want it to start one task. We want it to contain one physical core, and we want it to contain one GPU. And so you can see how the resource set's altered in the layout there, so that now a resource set has a GPU, and it still has the same physical core. But you can see this way how we can control what we have, and we don't have to take defaults. So you don't, in the previous example, if you needed a GPU and you were expecting it to be there, then you would wait in the queue, and in execution time it would say, I can't run because there's no GPU here, because that resource set wouldn't have a GPU in it, and it wouldn't be able to see a GPU or access any of the GPUs. So now that this is a very basic example, only using one core, one GPU on the node. There's a lot of resources left there, but if you looked at your code and you said, okay, my code will perform best and is easiest and makes the most sense for each thread to communicate with a single GPU, or each MPI task or rank to communicate with a single GPU, then you say, okay, that's what my resource set looks like. So this will give you one of those. And now the next step is how can I expand this? So expanding it once you have the resource set set is pretty easy. You just then increase the number of resource sets that you want to run. So you can see in this example, we've increased our resource sets to 6. We didn't touch the number of tasks or physical cores or GPUs. That remains the same. That's saying I want to start 6 resource sets now, but in each one I still want just one task, one core, and one GPU. And you can see on the diagram how we have our original red resource set, and in yellow we have the next resource set, and blue, and so forth. There are a lot of cores here, right? So when deciding how many of these resource sets we could put on a node, the limiter was the GPU. Since each resource set needed a GPU, 6 is the most that we can put on this node. But you can see how we didn't have to change what a resource set contained. We already knew that. We just said start more of them. And then they're started, and they each contain the same amount of resources. So the next step, expanding that. So there's a lot more cores on the machine, and maybe you need to run across more of those cores. And so again, now we just need to change one flag so that we expand what's available to a resource set. So -c it controls how many cores are in a resource set. So by expanding the cores to 7, then you can see we can now create resource sets that contain more physical cores. The issue here is that you still only started one task per resource set, but you have a lot of cores. So maybe this is helpful for layout, but most likely those are cores that are just sitting idle, and you didn't need to add them unless you want to request more tasks. In which case, you would need to specify increase the number of tasks as we did here. So you can see here we're still starting 6 resource sets. Those resource sets still have 7 physical cores, but now we've increased and told the system to start 7 tasks per resource set. And we left GPU to 1. And so you can see here how the system would lay this out on a single node. We've also added to this request the distribution of PACT. So this tells the system how to lay out tasks between resource sets. So PACT is actually the default, but again, good to just specify this on the command line, and then you don't have to worry about what the default is or if something changes it for some reason under the covers. So PACT basically tells the system to fill up the first resource sets with tasks before moving on to the next resource set. So you can see that here, the first resource set, the red resource set, contains tasks 0 through 6. So those are the first 7. It then moved to the next resource set, the yellow resource set, and placed the next 7, and so on until it got all 42 tasks placed. You can change that if you want, and again, we just changed this in one place, and each resource set will then resemble this change and be created in this manner. In this example, we left everything the same, but we changed our distribution to be more of a round robin. So we changed it to cyclic, which says place the first task in resource set 0, place the next task in resource set 1, and keep going until you've placed 1 task in each of the resource sets, and then come back around to resource set 0 and place the next task there. So it's more of a round robin fashion. So these are layout options that are available in MPI Run and other launchers. But with the added resource sets here, this kind of adds a little bit of layer of difference on top here. But I hope this is making a little sense as we go through. Again, these don't cover all the cases, but hopefully this gives you some examples of the basics so that you can then start playing around with additional layouts. So another thing that is commonly done, runs on the machine is the use of threads, is the use of codes that are written in a combination of MPI and OpenMP, for example. And so to run on threads, this example shows what a basic JS run would look like if you were to run a code that launched, that each MPI task launched 4 threads. So in this example, I grabbed 2 nodes just to show the layout, but kind of what it looked like between 2 nodes. I then set, before I ran JS Run in my batch script or in my interactive batch job, I set OMP num threads to 4 to tell the system to launch 4. And so we have 2 nodes. I need, for this example, to run for each task to launch 4 threads, and then each task needs to see 1 GPU. So to run these, I want each thread to land on a separate physical core. So when I set my resource set, I'm going to need to add 1 GPU. I'm going to need to start 1 task, and I'm going to need to add 4 physical cores. And that will give all of the threads place to launch on each thread on their own physical core. And again, I know because I need 1 GPU and only 4 cores that the limiter here per node is really the GPU. So I can launch 6 resource sets per node. I have 2 nodes, so I can launch 12 resource sets. So 12 resource sets, each one task, 4 physical cores, and a GPU. I kept the distribution of PACT, as you can see the last command there on the JS Run line. It's not really significant here because there's only 1 task in each resource set, so that doesn't really come into play. But the key here that you want to keep in mind is the binding. So you want to make sure that you throw the binding flag and tell it to bind 4 physical cores for each MPI task. And that way, it gives the system room to spread those threads out. You can see in the example over to the left that rank 0's OMP places in this case would be set to the first 4 cores and the threads on those cores. So another note, just to emphasize the importance of the binding flag. So the binding flag, when you run threads, you need to not only make sure that your resource set has enough physical cores to allocate and to spread those threads out, but you also want to control and set your binding so that those tasks have those cores and are bound to those cores so that those threads can be laid out. So when you run threads, you really need to use your -C cores option and your B binding flag. So the binding flag gives you some options for its what it takes. You can say binding of none, which means don't let the system do any binding. I want to do that myself. You can bind to a resource set, the -RS, which will bind to the full resource set. I've seen enough cases where it causes problems that I think it's not as a shortcut way as we would hope. So I think the best way would be to use the binding packed, where you say packed : and then the number of CPUs. And there's also a packed : SMT, where that is in the last item in that green box. It'll let you say not the number of physical cores, but threads instead. So these are the SMT hardware threads. So I've given in the black box a couple of quick examples just to show how leaving the binding off can impact a run. So in the first box, we set the OMP num threads to 2. We launch a resource set that starts 1 task, and that task is going to launch 2 threads. So we know we need 2 cores, and we allocate 2 cores to this resource set, but we don't do the binding. And so by default, the binding is packed 1. Packed 1, it doesn't change. It doesn't follow -C. It doesn't follow OpenMP. Your thread settings, it's just always the 1. So in this case, we didn't specify it, so it took the default. And you can see where it placed for that rank. It started 2 threads, but it placed them both on hardware thread 0. So now those threads are sitting on top of each other, and when you run, you will then have a runtime that's most likely longer than you expected because you oversubscribed resources. And in the bottom box, you can see how adding the packed 2 to say give me 2 cores for that, bind 2 physical cores for that hardware for that rank, and how it will lay out and give you a layout of the first hardware thread on the first core and the second hardware thread on the next physical core. So we've gone through some ways in the first part of this to say how JSRun will lay out and how you go through BSub to allocate resources. The next thing I think you're going to want to do is take those basic examples and begin to play around with that layout in JSRun and see how the different flags impact layout. You can probably do this. There's a number of ways here, and I think you can probably do it through an interactive job and just grab 2 nodes. With 2 nodes, it can tell you a lot. It can let you look inside a node, and it can let you look at the interaction between nodes as well. So you don't need a big allocation to grab an interactive batch job and run some examples and tests. So a few ways to run these tests through, you start an interactive job, and there's a few ways to see the layout that JSRun is creating. So the first case here that I give is a code that we've created internally and that we make available through a Git repository. And I placed a link there. If you just go to the Summit's user guide on the doc site, you can find it there, links to this code. You can grab it, compile it, and run it, and it will print, a layout similar to this. You can also see what it's doing and modify its, what it's showing, so that you can see the output maybe that you want. So in this example, I've shown the first box. I've used this example to show how not adding enough cores, physical cores to your layout can cause oversubscription. And so in this case, I've grabbed the first box, I've grabbed 2 resource sets and I've placed 2 tasks in that resource set, but I didn't specify the number of cores. So it will by default to take the default of one physical core. And so the system will only have 1 core to place these resources. And so it will place two ranks on a physical core. So you can see here how now you have 2 ranks on a physical core, which is probably not what you wanted. You probably wanted those on separate resources. The second box down shows how adding the -C can then allow that to be spread out, and each rank gets its own core. I've also added, played around with the -D to show how the cyclic and the packed layout looks here. So another way to look at the layout is to use the JS task info binary that the developers of JSRun provided. So this should be available in your path. It sits in the same directory as JSRun, and you can see very similarly. It also shows when you run this through JSRun, it will print out the layout. So in this first example, I printed the layout using pact1 and show and look at where the threads are set and where they are bound to, where OMP places is set to. I also, as a test, said, let me see what pact SMT4, because that's our default. And sure enough, it looks the same. So pact1, if you take the default of your LSF SMT4, looks the same as pact SMT4. And then the last example, I show what it looks like if you say pact SMT1. You can see how your OMP places has the first hardware thread on each core or on the core to see there. So another way that you can view layout is you can run an executable here, a tool that maybe vendors may provide. So in this case, I use the NVIDIA's SMI tool to see what GPU resources that my JSRun command could see. So in the first example, you can see I ran JSRun with 1 resource set, and no GPUs, and then I started a shell and executed the NVIDIA SMI command with some flags, and it reports that you have no GPUs, as I would expect. In the second example, I added 3 GPUs to my resource set using -G3, and it reports the 3 GPUs. In the final example, I need 4 GPUs, and then I played around and said, okay, let me get more cores and see what the layout looks like. And you can kind of see how the resource set was created, and you can see based on the bus ID of the reported GPUs that the first 2 are on socket 0 and the second 2 are on socket 1. All right, so the third way example here to look is another method that we've created internally. So this is a graphical tool that was created. So this is JobStep Visualizer. And so what this will do is allow you to, you simply load a module, which will set all the behind the scenes flags that you need. Then you run your JSRun command, and it will provide a link to a website. If you go to that website and follow that link, it will then show you in a graphical form where your job is laid out on the machine and how the tasks are laid out within each node. So you can step through your nodes and kind of see what it looks like. This is a nice way. if you want to double check a large run, you can do this. But it provides the same graphical layout that we went through in each step of this talk. So this is very nice way to kind of graphically view those and see how changes that you make to your JS run flags impact the layout. So now, let's see, we have 5 minutes. So I'll step through real quick. So there's another common thing that people do is run multiple JS runs within a batch job. So you can do this. JS run and the underlying CSM know where each JS run is running. So unlike systems that run just MPI by itself, where you have to control where those MPI runs are placed, JS run knows, and the underlying system knows where these JS runs are placed. So it will handle where they're placed and place them in a way that they're not sitting on top of each other, and it will internally queue them if there's no place to run those. So this is just an example of what I'm talking about. If you run this test, it will basically run all of these commands serially. So you would run JS run. The first one, when it completes, say it takes 25 minutes. Once it completes, the next JS run will start. It'll take 5 minutes and so on, right? And these will just run serially until each one completes. And so your total wall time for this job would be 1.5 hours. The other way to run this is to run JS runs at the same time. And so this way, you run a JS run and you simply place it in the background, and the system will run it and move on to the next task. And the next task is a JS run, so it will run that. There's room, it will place it, and keep going through. The key here is to make sure you add a wait to the end of your batch script to make sure that if without that wait, everything's in the background, and that script will reach the end and say, I'm done, and it will exit the queue and your job will be killed. So make sure you have a wait. That way the batch script doesn't exit before all of your backgrounded tasks. So when you place these in a wait, basically it lets it run the first command, the second command, and the third JS run there at the same time. So in this case, you can use more nodes, but have a shorter wall time because these are executed at the same time. So these are both equally useful. It just depends on what you want to do. And then the last thing just to say on the multiple job steps, if you did this interactive, this is kind of an example of showing and running these steps interactively for an example. And in this example, I ran cases that would not all fit. So the first job requests all of the GPUs on a single node. The next job doesn't need GPUs, but it needs all the cores on the node, so it can't fit on the first node. So the system places it on the second node that you've gotten, assuming this is a 2-node allocation. So now you've got a JS run on the first node using all the GPUs and just some of the CPUs. And then the next JS run you have a job that using no GPUs but all of the cores on that node. Now we submit another JS run to the system, and it needs just a single GPU and a single core. So there's cores available in the first node, but there's no GPUs available in the first node. The second node has GPUs but no cores. So because you can't create a resource set that spans nodes, this job has nowhere to fit. So basically what the system will do is place this job on kind of an internal queue. Once one of the jobs ahead of it finishes, then it will have a full node where it can be executed. And so I use there's a command that JS run provides. It's called JS list, and this command will show you the jobs, the JS runs that are currently running, queued, and in this case I ran a bunch of other tests, and so it would show the ones that have completed during this batch job as well. All right, so that hopefully was not a fire hose worth of information, but that is kind of hopefully enough information to hopefully explain at a high level how you run jobs, how you utilize the compute resources on Summit, and gives you enough information to build on those and test and run cases that you need. JS Run and BSub have man pages. There's documentation on the web, on the doc site as well. And of course, we are here. You can email us to answer any questions. So I think I've used a good chunk of this time, but if there's any questions, this is a good time.